Now what is this thing? So let me just give the simplest examples. So suppose that this solution existed. It's kind of the simplest one I can draw. That's a running solution, running orbit. And what this orbit is in a little space is it enters from here, exits, re-enters here, comes back, exits. And it's a two-cycle. It's an orbit in a little space that after the second bounce, it comes back. First time it bounces, and then it's on the other side, bounces, comes back. You can already see that if I did this in fundamental domain of just a fixed point, it wouldn't recycle too, because you can see that this is the same as that. But at the moment, we are not being so smart, so we are only going to that thing. So this is not a prime cycle of dynamics. There is a shorter cycle that's being repeated twice in this particular example. Good enough for the military. So now what happens is that to come back, I see that I have to translate by the whole box by one. See, because obviously this is the same as this point. Now it repeats. So the two cycle you're looking in a big space is bounce here, bounce this guy, and now you're back and you move it by one. The distance between these 2 points is an integer vector, which is np. So this is the group transformation that you have to do. So you write your translation in the basis of 2 or 3 of these guys, depending how smart you want to be. And you realize that in terms of these basis vector, which are operations of the group, discrete group that move you back, this is an integer, because it's an integer time you're moving around, but it's a two-dimensional vector in this particular example. So that says that this weight that we are computing is actually weight of a prime cycle in fundamental domain is actually 1 over lambda, stability of that cycle, periodic orbit, its length in discrete time units, and its weight beta dot, a two-dimensional vector p, which is a group element in the translation group that puts anything to that. So it's just the vector that says wherever I end it before I start repeating my cycle, I just bring that back, and now it's periodic in fundamental domain. And the way you compute this number is that when you work in a fundamental domain, as you go through periodic orbit in the fundamental domain, every time you cross, you record the translation you needed to bring you back. So just accumulate it. So that's called the reconstruction equation when you have discrete lattice. It just says every time you have to do a group operation, remember it. Just store them and add them up. So this is a nice calculation for discrete maps because the time is integer time. And this thing here is do I really use ends for this? I guess I use ends. So this is time, and this is the thing with the hat is actually two-dimensional vector, which is a translation member of the translation group. So we have reduced the group of translations in this way. This is the discrete time. It's a number of bounces. And this is distance of relative, so global distance. So are you happy? Because the rest is kind of totally trivial now. I just take two derivatives of this and I get the answer. I can't do anything more. So it's really, really simple. It's still a two-dimensional parameter. The motion in fundamental is still two-dimensional, and beta is dual parameter to the distance. So it's still true. See, the real thing that's very baffling is that here I'm sitting on a little space, and I'm obviously not diffusing because I never leave it. So, in this space, the notion of diffusion makes no sense. It only comes through the fact that there is translational invariance, and that this is tiling of the space by translational invariance. So for example, we have to rethink this for continuous symmetries, but now it's very simple. So diffusion just came from the fact that I can unfold the motion on this and tile it, lay it out on the kitchen floor covered with hexagonal tiles. And this one, when you go from any problem that we have done so far to the fundamental domain, they have the same dimensionality. The only thing that changes is the size of the state space. Because you made state space smaller because you can tile the big thing by copies of the small one. So it's still true that you're looking at x. It's still true that you have x, but now it's called tilde, x of t. So you're moving here in 2 dimensions. And then various things happen according to your laws of reflections, etc. This guy is still in 2 dimensions. We are only looking at configuration space, but not momenta. So you're not looking at momentum space because of elastic collisions, the momentum doesn't change, the magnitude. So the only thing that matters is theta. The only diffusion that can happen in this model is only in space. There are other models in which you have something oscillating, you vibrate it by external force, and you actually induce diffusion in momentum space by making it go oscillate faster, etc. That's not this problem. That's a different problem, but same techniques can be used. So this is still in the plane. It's related to this one in a way we know from the 3-disc billiard. We have done it. Now it has more tiles than the other one, but it's the same problem. So you can call this a phase. Discrete translations in this case a phase. Just a little bit more intricate than the thing that you did for 3-disc billiard. So you'll figure out the relation between the two. You'll just have more symbols. Before we only kept track of 3 neighbors, but now we have to keep track of 6 close neighbors and then 6 more distant neighbors. So in one flight, I can hit any of these 12 guys. So it just gets more laborious, but you'll be able to do it. So there'll be symbolic dynamics, and when you reduce it, there'll be 11 symbols here. Before you had 2 symbols, basically, and when you reduced it, you just got binary dynamics. I mean, you had 3. Here you'll have side with stealth, you'll get 11. And you can do it. It's just more laborious. And you keep track of each symbol tells you to which neighbor you went. So that's totally crucial to go from here to there, because it'll tell you in which part of this thing you will be. And that you need for your global diffusion. So it'll be there, it's just a little more work. So the problem set I gave you, it will be very simple. It's one-dimensional. It won't be so nasty as this one. You can do everything by hand because it's analytic. So it's linear maps, and you'll be able to do it.